In a perfect world, axial column loads are applied exactly on the column's centerline. However, in reality, it is impossible to be so precise. As a result, columns experience axial loads that are applied at an offset from their centerline. This offset creates a small moment that forces the column to rotate. If the column is unable to resist the rotational force, it will buckle. Because moment equals force, P, times the distance or displacement, R, the moment will continue to increase as the column buckles, which in turn causes the column to buckle faster. As the column continues to buckle and displace further from its original centerline, the moment continues to increase, which consequently increases the compressive stress faster and faster, until the column reaches a point of critical failure. Another factor affecting a column's ability to resist buckling is known as the slenderness ratio. The slenderness ratio is a function of the thickness of the cross-section and the effective length of the column. Rectangular and square columns pinned at both connections will have two slenderness ratios, one for each dimension of the member, shown here as B and D. The slenderness ratio is equal to the length of the column, LE, divided by each dimension, B and D. When evaluating a column for buckling strength, the highest ratio must be used for subsequent calculations, as that is the axis in which the column is most susceptible to buckling. This 2x4 member is most likely to buckle across the dimension B. Similarly, another column with the same cross-sectional area, but a longer effective length, will have a higher slenderness ratio, and be more susceptible to buckling when placed under the same load. However, if we need to decrease the slenderness ratio of the column, but cannot decrease its effective length, we can do so by increasing its cross-sectional area. In this case, we can substitute a 4x4 member. If a larger member is unavailable, we can also reduce the slenderness ratio by bracing the column. In order to better understand these concepts, let's take a look at a practical application in construction, elevated slab formwork design. In this example, 2x4 timbers are being used as formwork shoring for the elevated slab. However, because the shores were not properly sized or spaced to handle the load, they buckle. It is important to note that even if a column only buckles but does not break completely, it is still considered to have failed, as it can no longer reliably support its original intended load. Inadequately selected column size or spacing in a formwork system can lead to the collapse of the elevated slab, as the columns buckle under load. An incident such as this on a job site is not only a safety hazard, but will result in unforeseen costs and delays to the project. There are several alternatives that could have been used to prevent the shores from buckling. The first alternative is to reinforce or brace the shores, which reduces the slenderness ratio of each shore. Another method is to select thicker shores, which also reduces the slenderness ratio in each shore. Lastly, the spacing of the shores can be adjusted. However, the best alternative is to properly design the shoring system from the beginning, to prevent a costly and dangerous incident from ever occurring.